Yesterday, I defined with you what a representation is and just some basic terminology of representations. What are sub-representations? What do you mean by irreducible representation? What do you mean by a reducible representation or a completely reducible representation? Some basic terminology. And now I will give you the connection between representations and modules. Which was seen for the first time by Burnside, and then followed up with Eminoider, who did a lot of great contributions in this area. So the link of representations and modules has been obtained by rings called so-called group algebras, which I sort of introduced as a vector spaces yesterday, but I will recall that for you or do it again for you. So what is given a group G and a field F? I've taken a field, although group rings are also defined, but I'll be just concentrating on the field F. So G for me is a finite group, but group ring is defined even for arbitrary groups. So, but I will concentrate on finite groups and representations over fields. So G is a finite group, and the elements of G are listed as, say, G1, G2, Gn, and F is a field. Then what is Fg? You take formal F linear combination of elements of G. This is a vector space over F with the group elements as bases, as we saw in the regular representation yesterday. We took this vector space Fg, formal F linear combination of elements of G. Now, this Fg can be given the structure of an algebra over F in a very, very obvious manner using the group multiplication and associative laws. And of course, the field F as follows. So if I have two elements of Fg, so these are two elements of Fg, how do you add them? You add them component wise. You add the corresponding component of each group element. And how do you multiply them? You multiply them using the group multiplication and the field multiplication, and you assume that the group elements and the field elements, they commute. If they don't commute, then I will not go into the cross products and so on. So I assume that a field element commutes with a group element, and so when I multiply any two elements, the multiplication is like this. Now Gi Hj is some Gk. So so this is the coefficient of Gk, which I can collect because the addition is component wise. And how is the scalar multiplication defined? This is an element of Fg. And how do you multiply it with a scalar lambda? Lambda is from F in the obvious manner. And so with this addition, multiplication, and multiplication by elements of F, you can check that Fg is a ring, Fg is a vector space over F, and this becomes an algebra over F. So this is called group algebra of G over F. For example, say, let's say your group is, say, Klein's 4 group, Z2 cross Z2. Its elements are written as 1, A, B, and AB. So whatever way you want to write down its elements. So what will be, say, let's say I'm talking of complex group algebra. Then its elements are complex linear combinations of these 4 elements. And the addition is component wise, multiplication is using the group multiplication. For example, these are 2 elements of CG. How do you multiply them? In a very, very obvious manner. But now you have to use the BAB. But now this is A square. A square is identity in the group. So this is just B. This is B. A and B commute. So this will become A. B square is again 1. So this fellow is 2A plus 2B. So this is how you have to multiply the group elements using the multiplication of the group. Now, so having obtained this ring, so I have a group G and I have a field F, and I have obtained this group algebra of G over F. So I can talk of the modules over this ring, modules over this ring. And so there is the theorem says that there is a bijection between representations of G over F and Fg modules which are of finite rank over F. So between these two sets, there is a bijection. So you can go from representations to modules, modules to representations, but modules, because my representations are over finite dimensional vector spaces. So Fg modules should have finite rank over F. So this is what you want. You have two sets S1 and S2. On one side, on the set S1, I have representations of G over F. And here I have Fg modules which are of finite rank over F. Okay. Let us prove this correspondence. How do I go from here to here and from here to here? So here is a representation T from G to GLV. Now, how do I construct a module, Fg module, which is a finite rank? You take the same V. V is a vector space over F. The same V, which is a vector space over F, I will convert it into an Fg module. So how do we will regard V as Fg module as follows? So what do you need? You already know how the elements of F and the elements of V multiply. So all you need to define is what is G dot V. How do group elements multiply with the elements of the vector spaces? Now from a group element, I can go to a linear transformation from V to V. So look at this linear transformation and apply that on V, and you can check that V becomes extend this linearly on Fg. I've just defined it on G. Extend this linearly on Fg and check that V becomes an Fg module. And the dimension of V over F is finite is already there with me from the beginning. So I have this, and so I've given you a map from S1 to, this is my element of S1, and I've given you an element of S2. Now conversely, suppose you are given V, which is an Fg module, and the dimension of V over F is finite. I want to construct a representation. So basically, so I have to give you a homomorphism from G to, I will use the same V. V is an Fg module, therefore V is also an F module. V is a vector space over F, and the dimension of V over F is already finite given to you. So given G, I have to give you a 1-1-on-2 linear transformation from V to V. So you define Tg. Tg of V is defined like G dot V, because I know V is an Fg module. I know G dot V because V is an Fg module. So this makes sense. This is coming from this action of Fg on V. And this is a 1-1-on-2 linear transformation because G is invertible. Tg composed with Tg inverse is identity, and therefore this is a 1-1-on-2 linear transformation from V to V. So this Tg defined like this is an element of GLV, and there is a map from here to here. And now you can check that the composition from both sides. If I start from here T, I go to V and then come back, I will come back to the same place. It is identity. And if you start from here, come here and then go here, you will go to the identity of S2. So these two maps are inverses of each other, and therefore there is a bijective correspondence between representations and FG modules, which are of finite dimension over F. Okay. So for example, let's say we saw this a representation of D4. Okay. We saw this is a representation of D4 and dihedral group, two-dimensional, and look at what is the corresponding FG module. What will be the vector space? You are in GL2F, the vector space will be two-dimensional vector space over F. V is your F2. Okay. And how this becomes an FG module? G dot A. I'm writing the elements of F2 as column AB. This is an element of F2. So G dot AB is, you have TG, you apply this on B. So basically you multiply this with this, and this is how you regard F2 as FG module. So this is the way you define. And conversely also, if you are given V, which is an FG module, if V is given as an FG module, then you can construct vector space exactly the way I explained in the bijective correspondence. Okay. As another example, just look at the permutation representation. What is a module coming from permutation representation? You have a representation from Sn to GLNF. So your vector space is Fn. Okay, Fn, and G dot V1, V2, Vn. The action of G on V is like TG on V1, V2, Vn. For example, let me take an example. Say suppose N is 4. Suppose N is 4. Okay, and say G is your cycle 1, 2, 3. Now what is G V1, V2, V3, V4? Okay, this will be V2, V3, V4, and V2, V3, V1. Okay. And then V4 is kept fixed, so V4 will go to V4. So this is the way it works. If G is say 1, 2 into 3, 4, then this V1, V2, V3, V4, and G dot this will be V2, V1, and V4, V3. So this is how this becomes an FG module. Okay, so now look at, so now I have given you that there is a 1-1 correspondence between representations of G over F and FG modules, which are of finite dimension over F. Now look at the group algebra FG and FG as FG module, as a left FG module. FG can be regarded as a left FG module, and the dimension of FG over F is finite. It is how much? It is the order of G. Therefore, it corresponds to a representation of G over F. What is that representation? So, what is the representation corresponding to FG as left FG module? This is what I am asking. My G is a finite group. Throughout these lectures, your groups are finite and vector spaces are finite dimensional. Okay, and the answer is, what do you get is the regular representation. Can you see that? Just look at the way we have defined. Look here. So I had FG as FG module. And the way I explained to you, construct a representation. How do you construct a representation? From G to GLNF. What is this N? It is a dimension of this vector space, which is the order of the group. G goes to TG, and TG on V. I'm just taking basis elements are group elements. So I'm just computing this on basis elements. And this is what I defined here. Look here. This is what I defined in the correspondence, that this is the representation corresponding to corresponding to this vector space. This is the representation. So exactly the same way I'm taking V as FG. That's it. So if you take V as FG, then what you get is the regular representation of G over F. So I hope this is clear. All right. Now, in this correspondence, how do equivalent representations behave? How do isomorphic or irreducible representations behave?
Ma'am, may I interrupt for a minute? Just for a second. Sure. Yeah, somebody raised a hand, so
sure.
Can I allow her to talk?
Yes, please.
Yes, Manideep. Yes, Manideep, please go ahead. Go ahead. Ask a question. You have been raising hands.
Yeah. Am I audible?
Yes. Go ahead.
Okay. So in the 11th slide, ma'am, where you have computed, taken a cycle, can you please go to 11th slide?
11th slide. Yeah.
Yeah, where G operated on, in the last line, G operated on the V1, V2, V3, V4, where G you have taken as the 3 cycle, 1, 2, 3. So
Yes.
how you do this computation? Because I think that since 1 go to 2 and 2 go to 3, so V1 will go to the second position, and V2 will go to the third position, and V3 will come to the first position. So I thought it would be like V3.
Yes. Yeah. You're saying it right. Yeah, true.
Okay, so I mean, then it is V2, V3, V1. You have written that V2, V3, V1, and V4. So yeah, I think
it is this. Let me write down. What is the matrix of this G? V1 goes to V2. So this is the first column. V2 goes to V3. This is the second column. V3 goes to
and V1, and the fourth will be unchanged.
Yes. So you have to multiply this on V1, V2, V3, V4. Yes. Okay. Okay. So you are right. That was the type. Yeah. Thank you. So what will you get now? V3.
V3, yes. Then
V2, right? Sorry, V3, V1, V2, and V4.
And then V4.
Yes. Yeah, right. Thank you.
Thank you, ma'am.
Yeah, that was the type. Yeah. Thank you. Anything else? Is that okay?
Yeah, ma'am. It's okay.
Okay. Thank you. Yeah, I'm glad that you are checking the calculations. Yeah, thank you. All right. So now I was here, right? So I want to see. So here are representations, and here are modules. In S2, I am keeping modules. In S1, I am keeping representations. So if I give you 2 equivalent representations, And then what I want to see is that they correspond to isomorphic modules, and vice versa. If I take isomorphic modules, then I will get equivalent. The corresponding representations are equivalent. So very nice correspondence. So let us write down. Suppose T and S are, let me write down T. T is from G to GLV, and S is from G to GLW. Suppose these are equivalent. Then I want to prove that the corresponding modules are isomorphic. Now, what is the module corresponding to this? The same V regarded as FG module, and the same W regarded now as FG module. V is isomorphic to W as FG module. This is what I want to show. All right. How do you do that? Let's go to equivalence. This is my notation for equivalence. T is equivalent to S implies that there exists isomorphism phi between vector spaces. Isomorphism as vector spaces, as F vector spaces, such that what happens, that TG composed with phi inverse and phi gives you SG for all G in G. So what I will show to you, that the same mapping phi from V to V, which is an isomorphism as vector spaces, is also an FG isomorphism. So basically this map phi is also G linear. So if I prove to you that this map phi is G linear, then this will become a G homomorphism, and it's already 1 on 2. And therefore, this will become an isomorphism as FG modules, right? So what I want to prove, that this map phi is G linear, right? So this follows from this part, what is given to you. So you apply, this is my star. So I will derive this, whatever I want from this star. Now you apply this on phi V. So you take an element V in V, and now you apply this on phi V. Phi V is an element of W. So SG on elements of W I can compute. So I can do this. This is true for all V in V. And so this gives you phi TGV is equal to SG phi V. Now this is your understanding. How do you regard V as FG module? This is, if you regard V as a FG module, then this is your definition for G dot V. And if you regard W, this is an element of W, and this is the meaning of G dot W. Okay, this is how you regard W as FG module. So phi of, so basically this is nothing but saying that the map phi from V to V is also G linear. Okay, so phi is G linear, 1 on 2 was already there, so it's an FG homomorphism, and therefore it's an FG isomorphism, right? And conversely, exactly the same thing can be done, but let me, if V and W are isomorphic as FG modules, then you have phi from V to W, FG isomorphism, and therefore phi of G dot V is G of phi of V. But this is precisely the same thing. I can do the same thing, because this is the meaning of that. Okay, and this is precisely what do you mean by saying that T and S are. So this means that the corresponding representations GLV and S from G to GLW defined by G goes to TG, G goes to SG, and TG of V is G dot V, computed like this. W is G dot W are equivalent. So precisely the same thing can be said backwards. So, all right. Now, stop. All right. Now, where am I? Okay, I want to now define, I want to show you that under this correspondence, irreducible representations correspond to irreducible modules, right? So what is an irreducible module? So-called simple modules. Are you familiar with this term? Simple modules or irreducible modules. So a module is called irreducible if there are no submodules other than 0 and itself, right? So V is an FG module. V is irreducible FG module if 0 and V are the only FG submodules of V. Right? So representation is irreducible if and only if the corresponding modules are irreducible. So the correspondence is beautiful. Equivalence corresponds to isomorphic modules. Irreducible representations correspond to irreducible modules. So I'll just quickly show one way, and the other way you can do it yourself. That suppose T from G to GLV is an irreducible representation. So what do you mean by saying that you have an irreducible representation? That there is no T invariant subspace of V. Okay. So to show that V as FG module is what? Irreducible. Right? Suppose not, what will happen? Then there exists a submodule, FG submodule, W of FG module V, and W is different from 0 and V. This is what do you mean by saying that a module is not irreducible? Okay. So if that happens, then what do you have? G dot W is FG submodule. So that means G dot W is an element of W for all W in W and G in G. In fact, if I operate alpha elements of FG on elements of W, I will still land in W. So in particular, I have that G dot W belongs to W, right? But now, what is this? What is this? This is your definition of TG. TG of V is G dot V. So this means that TG of W belongs to W for all G in G. This is the corresponding representation. Okay, I started with the representation, right? So TG of W is contained in W. So this means that this is true for all G in G. So what does this mean? W is T invariant. So this is what I defined yesterday. What is a T invariant? This is your representation. A subspace W of V is called T invariant if TG, all linear transformations TG, which are from V to V, if I apply them on W, I should land them in W. So that restriction is an endomorph is in GLW, is from W to W, and therefore it lands in GLW. So W is T invariant. So and conversely, the same steps you can if W is T invariant, then this will happen, and then W will become an FG submodule of the same steps you can trace backwards. And therefore, you can prove that the irreducible representations correspond to irreducible modules, right? Now, let's see some examples. Okay. Now, let's see. You have a trivial one-dimensional representation. What is the module it will correspond to? It will correspond to, you have a trivial representation of, you have from G to non-zero elements of F by mapping G to 1. All G is going to 1. What is the module you are going to get? What is your vector space? This is GL F. So your vector space V is F. How is it regarded as FG module? G dot V is V. Via this G dot V is V, because it's identity, it goes to 1, and so this is trivial FG module. So if the module which you get from trivial representation, trivial one-dimensional representation, is F as a trivial FG module. Okay, and F as a trivial FG module is irreducible. You can prove yourself because it is just one-dimensional over F, and trivial representation is irreducible, is clear. So you see that corresponds. Okay, so now look at the representation of D4 which we saw yesterday. We saw that from G to 2 degree representation we saw, maybe over complex numbers I'm just talking of, say, or over here is anything will work. Okay, so because I was just giving you one linear transformation from R2 to R2, so that's why I just took. So what was that map? A goes to, say, we send A to the 90 degree rotation, right? So 0, 1, minus 1, 0. I hope I am right, but if there is anything, any typo or anything, please let me know. So this is on the diagonal. B is going to the projection along the diagonal, and A is going to rotation through 90 degree of R2. And we saw that this is a linear transformation. This is a representation of G. And now what is the module you are going to get? V will be your R2, R cross R. And how do you, just now we saw, how do you regard V as RG module? Say V as RG module is that A dot elements of V I will write as columns alpha beta, and so 0 1 minus 1 0 and alpha beta. So this will be minus beta alpha, and B dot this is what will be 0 alpha beta will be minus beta minus alpha, right? I hope this is correct. Yeah. Now you can let us try to see that this representation of T is irreducible by looking at the corresponding module. What will be your module? Your V will be R2. Sorry, I've already written here. This is my V is R2, and this is how it is regarded as an FG module. Now V as RG module is irreducible. Why? Because suppose W not equal to 0 is a subspace of is RG submodule of V, then you take a non-zero element alpha beta in W not equal to 0. Now, if this is in W, then A dot alpha beta is in W. So these two elements are in W. And these are in W, and you can prove that one of either these two or these two are linearly independent, depending upon the cases. So you always get that there are two linearly independent elements in W, and therefore W will become the whole of R2, which is your P. So if there is a non-zero submodule inside, then that has to be the whole of V, because it will contain two non-zero. As soon as it has one non-zero element, it will get two linearly independent elements inside, and therefore it will become the whole of V. So this proves that this 2-degree representation of G is an irreducible representation by seeing the corresponding module. Or you can do it directly, but because I'm explaining you the correspondence, so you can see from this correspondence, right? All right. So let's see a reducible FG module, or just to give you some flavor. Look at G is equal to S3 and V is equal to. Look at G is equal to S3 and V is equal to F3. Okay. Now sigma dot V, this is A1, A2, A3 is an element of F3. Sigma dot this is A sigma 1, A sigma 2, and A sigma 3. And now you look at the subspace where all of these entries are same. So it's like alpha, alpha, and alpha. All of these are equal. Then this is an FG submodule of V, which is different from 0 and V. So this is not irreducible. Okay, so there is a submodule different from 0 and V. So because you can see that you operate whatever sigma you operate on this W, this is not going to, whatever permutation you give on 1, 2, 3, these entries are all equal, so they are not going to, so it's not going to change. So it's a one-dimensional subspace inside V, and it is different from 0 and V. So this is a reducible FG module. All right. Now, so my so I have from representations, I have gone to modules, G to GLV, and same V as FG modules. Now I will use this theory of modules, and I will see when can I decompose this V as direct sum of FG modules. When is it possible for me to decompose V as a direct sum of FG modules? These are so-called semi-simple modules. I will just describe them in briefly. And so whenever you can decompose V as a direct sum of FG modules, then you can decompose T as a direct sum of, suppose T1 is representation corresponding to V1 and T2 is a representation corresponding to V2 and V1. So then you have decomposed your T as a direct sum of representations of smaller degree. So my question of understanding representations of G over F and decomposing a representation into sub-representation, I will shift to when can I decompose FG module as a direct sum of submodules. So what are the conditions on G and F which ensure that any FG module is a direct sum of irreducible submodules? So called when is, so basically I will see the question, when is the group algebra FG semi-simple. Okay, so here is what I was describing. Maybe let me say it here. This is a representation, and I have regarded V as FG module. Suppose I can write V as a direct sum of two submodules. Now you look at T1, because V1 is FG submodule of V. So V1 is T invariant subspace. V2 is also T invariant, as I said in the correspondence, that V1 is an FG submodule of V will mean that V1 is a T invariant subspace. V2 is a T invariant subspace. Therefore, you can talk of the sub-representation of T, the restriction of T on V1 and the restriction of T on V2. These are two sub-representations of T, and these are actually equal. So it's a small check. You can see that these representations are same. These two representations are same. If I take them in the matrix form, then they will be just equivalent representations. Okay. So by choosing the bases in such a way, you can say that they are same. So this is the same thing, but now instead of two components, I have decomposed V into FG submodules. Then my T breaks as a direct sum of sub-representations. So this is my next question. So when does it happen that a given FG module breaks into a direct sum of irreducible FG submodules? And so such modules are called completely reducible modules, semi-simple modules. And this is the next question. If there is any question till now, maybe you can ask. Is there any doubt till now? Okay, so I'll move further. So G is a finite group and F is a field. Characteristic 0 or co-prime to the order of G. Then I will prove to you that this condition is sufficient for this FG module V to have the property that whenever I have an FG submodule W of V, then it has a complement. That under these conditions, G is a finite group, G is a finite group, F is a field of characteristic 0 or co-prime to order of G. Whenever V is an FG module and whenever U is an FG submodule of V, then you can always find an FG submodule W such that V is direct sum of these two modules. My aim is to decompose V as direct sum of irreducible submodules. So these conditions are sufficient for V to have the property that every submodule has a complement. This you say that U has a complement, that U direct sum with another FG submodule is V, then you say that U has a complement. Okay. So, all right. So let's prove this. So if you have basically, if every FG module has this property, then it is actually Mesheke's proof that these are also necessary conditions that either the characteristic of F is 0 and co-prime to the order of G, but I am just doing the sufficiency that if this happens, then you can decompose. But if every FG module has a property that every submodule has a complement, then these are also necessary conditions, but I will not go into that proof. I will just take the sufficiency and assume under these conditions, we will be computing. Okay. So, but you can read the proof that this is also necessary for this to happen for every FG submodule.
Ma'am, sorry for interruption. Can I ask you a question?
Yes, sure.
Yeah, in the previous slide, you want to break V as you want to write V as direct sum of two irreducible submodules, right?
Two or a number of irreducible submodules. Yeah.
Yeah. So you have taken in the condition you have taken U as any FG submodule. Is it any FG submodule or irreducible? Condition you need to take that.
Where is it?
Uh,
This V?
no, in the next one.
In the next one. No. If V is irreducible, then there is no submodule other than 0 itself.
No, not V. I mean U.
U is any. U is any. U is for
Any.
the time being, it is any, but then I will keep on decomposing and then I will prove that eventually, because the distribution of Q over F is finite, so you will reach at a stage where you have decomposition into irreducible submodules.
Okay.
what here, yeah, here it is any, that any FG submodule has a complement.
Okay.
Okay, and then so I have broken this into two FG submodules, and then now you can apply the same thing to U. You just take a submodule of, if U is an irreducible FG module, very good. If it is not, you will break
Then
U
we can
into,
again break it into
again
two.
into two
Two or
submodules,
many.
and
Yeah.
two or many, and so this process can be applied. But since the dimension of V over F I'm taking as finite, so
So
this
it will terminate in one stage.
yeah, this process will
Okay.
stop, and so you have written V as a direct sum of irreducible submodules.
Okay. Thank you.
Okay. All right. So let's write down. So how do you write? This V is an FG module. So the conditions are clear to you, that characteristic of F is 0 or coprime to the order of G. Then you want to prove that given any FG module V and a submodule U of V, then it has a complement, that there is another submodule which has this property. Okay. All right. So U is FG submodule of a given FG module B. You see, F complement you can directly, by extending basis of V. Suppose you have a basis of F basis of U, say U1, U2, UM, and then U1, U2, UM, you can extend it to a basis of F basis of V. And so you can always find an F subspace such that V is U direct sum with that F subspace. That is possible. Okay. But what you want is that this is an FG submodule, right? This is my issue. Right? So we can always find a subspace. So by extending a basis of F basis of V, we can always find subspace W of V such that U direct sum with that. But my issue is I want an FG submodule here instead of just an F subspace. I just want an FG submodule. So you look at the projection from V to V by projecting element of V is uniquely written like U sum W because of the direct sum. And so I project this on the first component, which is U. So this is an F-linear map because this decomposition is decomposition into F subspaces. So this map is F-linear. Now I will produce an FG linear map, which means an FG homomorphism as follows. So you look at this map. I will look at this map pi star from V to V. V going to I want to make this G linear, right? Order of G is invertible in characteristic of F does not divide order of G. So order of G is invertible in the field. If the characteristic is 0, it is already invertible. And if the characteristic is non-zero, because of the fact that the characteristic does not divide the order of G, it becomes invertible. All right. So this is G inverse. Where is I of GV exists because of this is my V. This is my V. This is I'm writing. I'm sorry. What happened? So this is my V. Sorry. So this is if you have V, I will write down V is U sum W. Okay, V is U sum W. So you pi of GV you take. GV is, you have to decompose this as a component in U and a component in W and project it onto the Uth part. So this is that. Remember, this is not GU because V is U sum W. So GV is GU sum GW. This is definitely in U, but this is not necessarily in W. This is the problem. This is what we want to do. So this is not necessarily in W. So this may also have some part in U. So you have to write this as something in U plus something in W and project it to the Uth component. So you look at this map. And now pi star is FG linear, FG homomorphism. You can, maybe I can do it quickly for you. So you just take X in G. This is 1 upon this, sum G in G, G inverse pi of GXV, right? This is the definition. This is the definition. And now I will do it like X inverse G inverse pi of GXV. Now this is independent of G, so I can bring this out. And now if G runs over all the elements of G, then so does G times X. So this is basically nothing but what? Pi of V. Pi of V. So this is X, this along with this, it is pi of V, X pi of. So pi star of, so it's a G linear map. And what else do you want? You want a complement, right? Therefore, its kernel is a kernel of pi star is kernel of pi star is FG, some module of image of pi star. Image of pi star, for the time being, you can see that where is the image? Actually, image is lying in U because this is an element of U. This is an element of U. This is an element of U, and U is FG submodule. So this is still in U, and this is everything is still in U. So it is clear that the image of pi star is contained in U, but then this is contained in U, but then you can also prove that image of pi star is equal to U by proving by showing that pi star of U is equal to U for all U in U. Because let me tell you the reason. Because suppose this I begin with an element of U. If I begin with an element of U and W part is not there, then it is G of U. G of U is an element of U because U is FG submodule. So pi star of G of U will be G of U. Okay. So this will be nothing but some G in G, G inverse GU. Because GU is an element of U. So pi of GU will be GU itself. And so this is back U. This is back U. This is back here. I hope I have made this clear. So pi star of U is U, and therefore the image of pi star is actually equal to U. And now you can show that V is equal to kernel of pi star direct sum with U. U is an FG submodule. Kernel of pi star is an FG submodule because it's a kernel of an FG homomorphism. And now you can prove that this is a direct sum by showing that if I take an element V in V and V minus pi of V is an element of U. If I apply pi star on this, what I get is pi star of V minus, pi star of V minus pi star of V. But pi star of V is an element of U and pi star is identity on U. So this is basically 0. This is pi star of V back and this is 0. So V minus pi star of V is in the kernel of pi star. And so V is contained in kernel pi star, some U, and therefore you, maybe my V and U are looking same, but you please I apologize for that. If there is any confusion, you can raise your hand and ask if there is any confusion, and therefore you will have the equality because this is there. And direct sum, you can prove that there is nothing in the intersection of these two because of this property, and therefore it's a direct sum of FG submodules, right? There's a direct sum of FG submodules. Therefore, you have produced another FG submodule, which is a complement. Now, I want this is a consequence of Mesher-K's theorem that if G is a finite group and F is a field, which is either characteristic 0 or co-prime to the order of G, and V is an FG module, then V is a direct sum of irreducible FG modules. I have taken the dimension over F to be finite, and then V is a direct sum of irreducible FG modules. The way I explained that you decompose it, take a submodule, have its complement, write it as a direct sum. If both are irreducible, good. If something is not irreducible, again decompose, and because of the finite dimension, the process will stop at some stage, and you have decomposed your V into irreducible FG submodules. Very good. So if I have decomposed V as direct sum of irreducible submodules, now you look at the corresponding representation. So the representation corresponding to V, representation corresponding to V1. Every FG module which is finite dimensional gives you representation corresponding to V2 and Vn. And your representation, because now irreducible modules correspond to irreducible representations. You have already proved that. So you have decomposed a given representation into direct sum of irreducible representations using your study of using basically Mesher-K's theorem. So this is where you have landed, that you have decomposed under these conditions, and you have decomposed T into direct sum of irreducible sub-representations. And so now I will concentrate on when you have the field of complex numbers, the representations are called complex representations. If you have field of rationals, representations are called rational representations, reals, real representations, and so on. So what I will concentrate on is that if you take the field of complex numbers, say, so let's answer how many irreducible representations are there, what is the degree of their irreducible representation, what are their characters, what is their character table, and so on. And so this theory will change totally if you change the field. As I told, if you look at complex representations or rational representations, over complex, I will prove that every abelian group has linear representations, but over complex cyclic groups will have of more degree. Yes.